So let's just look at these couple of graphs. I'm going to go through these two with you, and then the rest of these you can kind of look through on your own, make sure and check for perpendicularity, and then I will we'll go through in the end to make sure that you get it. We're not spending all class on this, so we're going to spend just a little bit of time. So the basic strategy, I'm going to figure out the slope of both of these lines. And for each problem, I'm going to figure out the slope of each line, and then I'm going to multiply them together. So if I call this one right here line A, and then I call this one over here line B, so I want to figure out the slope of A. Let me write that down below. The slope of A, and I want to figure out the slope of B. And then I can just multiply it. Okay, that slope, I mean, that blue is kind of hard to read, but I'll make sure it's clear. All right, so let's just start with A. A is this negative slope. So I want to figure out from these 2 points, and notice some of them have the points provided, some of them do not. It doesn't matter, we can work with it either way. And we'll see that in the next one, what we're going to do. Okay, so we're going to start at this point, which is negative 3, negative, that should be positive 2. But anyways, we can correct that real quick. And voila, there it is, positive 2. So negative 3, 2, and we're going to come down to 1, negative 2. So the rise is just going down, and in this graph, every 2 grid lines counts as 1. So don't get confused by that. So I'll just kind of count this down as we move over. So I'm going to go down 1, 2, 3, 4. And there's my rise. Sorry, that's a rise of how much? Negative 4. Perfect. My run is going to be going this way. 1, 2, 3, 4. So positive or negative 4 there? Positive 4. So my slope, and I'm not even going to worry about simplifying this, really. My slope for this is going to be negative 4 over 4. Rise over run. And you've been finding slope for many, many years, so this should just be, yeah, we know how to find slope. That's all well and good. Okay, let's look at the blue line, line B. So starting, and I like to go left to right, so I'm going to start at this left point, and I'm going to do my rise and then my run. So I'm going to have to go up first. I'm going to have to go up 1, 2, 3, 4. So that's positive 4. And then I'm going to go right 1, 2, 3, 4. So that is positive 4 right there. So this is now going to be 4 over 4. Any questions on that part of it?
Where's the negative 4?
The negative 4 is because we went down. We had to start at this point, we went down, so that's negative direction.
So for blue, that's also true, or is it positive?
Well, we started at the bottom, we went up.
So you're going up.
Yeah. Okay, so now what we want to do is multiply these slopes together. This is going to be our test. Now, you might know already whether they're perpendicular or not, but there are going to be some that you need to multiply together in order to get your answer. So just get into the habit of doing that. So I'm just going to take slope of A, which is negative 4 over 4, and I'm going to multiply that by the slope of B, which is 4 over 4. And that gives me, when I multiply across the numerator, that gives me negative 16. And multiply across the denominator, I get 16. What does that simplify down to?
0.
Negative 1.
Negative.
I mean, you can't.
Yeah, well, negative 1 over 1, which is the same as negative 1. And this is what we're looking for. If we get negative 1 when we multiply these together, what do we know about the lines? They're perpendicular. So these are perpendicular. I'll put yes right here. Yes, these are perpendicular. But some of them will appear to be perpendicular and are not actually. So let's check the next one. And if we have a line where they don't give us any points, then we can just find intersection points on our own. Let's start with line A. It's got this positive slope. it's definitely intersecting right here at 0, 4. And it looks like it's intersecting again at 3, 5. And then again at 6, 6. So I'm just going to put dots wherever it crosses an intersection. So right there, here. It doesn't matter. I don't have to get more than 2 of these, but we can identify there are 5 of them on the page. All right. Make sure your phones are turned off if that's yours. Go silence it. Okay. Well, let's think about this. We're going to take any 2 points, and we are going to figure out the slope. So going from this point, I like to go left to right. It doesn't matter if we go from this point to this point to that one over there, but any 2 points. So what's my rise getting from this point to this one? Up 1 over how far? And what does over mean? Left or right? Right. So we're going up 1, right 3. I'll just kind of show that real quick. There's your up 1, and then your right 3. So the slope, and I'll call that A. Slope of A is going to be up 1, right 3, which is 1/3. Line B, let's find those intersection points. We know it intersects at 0, 10. And as I come down, I'm looking for the next spot where it crosses, which seems to be right here, at 2, 5. And I can come down again. There's another one at 4, 0. So at 2, 5, I'm going to put a dot. And then at 4, 0, I'm going to put a dot. So let's figure out the slope. Going from this point 10, 0, or 0, 10 down to 2, 5, what's my rise? Down 5, and my run is 2 to the right. So down 5, right 2. What does that mean my slope is going to be? -5 over 2. Okay. Let's multiply these together. I've got 1/3 times -5 over 2. Multiply across in the numerators, I get -5. Multiply across in the denominators, I get 6. So are these lines perpendicular? No. They are not. They're close. The closer you get to -1, the more they'll look perpendicular. But these are not perpendicular. And that's the important thing for our purposes. Okay. So what I want you guys to do is to try the remaining 6. You might not get done with all of them, but we'll kind of talk about it in a few minutes and figure out which ones of these are perpendicular. Okay, so after the ones that we did together, just the ones right after that, is this one right here with line 1 and line 2, is this perpendicular? No. And you can visually kind of tell that they're not, but I want you to test with the slopes on the test. That's what you're going to have to do. Right here, are these two perpendicular?
Yes.
Yes, they are.
You can tell visually too.
Yeah, well, you have to be careful with checking visually to say that they are, because it can look really, really close. But if they're obviously not perpendicular, a visual check. So that it's kind of that weird thing where you can determine they are not perpendicular pretty quickly by a visual check. But to say that they are, that's not as reliable. Okay, the next ones. Right here, are these perpendicular?
Yes.
What about these? Okay. Both of these are perpendicular, in fact. So you should have had a slope for this blue line on the left right here of 3/2. So you would have had 3/2, and you would have had a slope of -2/3 for the other. So -2/3 times 3/2 would give you -1 in the end. So those are perpendicular. Okay, the last two.
I think the 1
Okay, this one right here? Are these perpendicular?
Yeah. Wait. No.
No, these are not. See, this is that visual check where it can throw you off because they look perpendicular enough to me, but these are not going to be perpendicular. You have a, what is it, a 7/6 slope right here. And this one, you have a slope of, what is it? -6. Yeah, it's -3/4. So when you multiply those together, your 7/6 times -3/4 gives you -21/24. And remember, I said the closer it is to -1, the more it's going to look perpendicular, but it's only perpendicular if it's actually -1. So no, these are not. And the last one, are they perpendicular? Yes, these are perpendicular. All right, so you got some practice with it. If you still have any questions, confusion on that, let me know. But now what we're going to do is we're going to spend the last part of class looking at our next quadrilateral. Yay! All right, everyone should look at this side of the page. So you should see the diagrams kind of matching up with this one. And we're going to do the reflections here really quickly. Remember, we're investigating a new quadrilateral each time we do this. So think about what quadrilateral this is going to be. Okay, I'm hearing you guys saying it. This is an example of a rhombus. Okay, and I know you guys are still maybe drawing those quadrilaterals in. I'm just going to add a few little notes here that these sides, I'm going to add in some congruency marks. And I'm going to add in even these angle markers. It doesn't tell us what the angles are, but it does show us congruence. All right. This one looks almost like a face when I draw it in. Okay. So here's one thing we can do as a shortcut. We already know that a rhombus is a parallelogram. So all the parallelogram properties are going to be true for this. I don't really need to check them. So opposite sides are parallel? Yes, that's true. Opposite sides are congruent? Yes, that's true. What are the other parallelogram properties? Nope. We have 5 total. I just put 2 down. What are the other 3? We have opposite sides are congruent. So what angle properties are true for parallelogram? Okay, guys, pay attention up here. This is kind of your test to see if you're remembering your parallelogram properties. Opposite angles are congruent. What else? There you go. Consecutive angles add up to 180. They're supplementary. And what's the diagonal property that we have? Diagonals bisect each other. These properties will be true of every quadrilateral that you see. Not every quadrilateral, but every one of them that I test you on. So if you know those 5 things, you are already going to be doing pretty well. You're going to have some place to start. But you need to know some other properties about rhombi. So let's run through the other. Are the adjacent sides perpendicular to each other?
No.
No. If they were perpendicular, they'd have to be 90 degrees for your corners. That's not the case, so we can say no. Are all 4 sides congruent?
Yes.
Yeah, and that is the defining characteristic of a rhombus. So if you look, I added those congruency marks in so you can see, and in the top one, 2 congruency dashes for every single line. That means all 4 of them are congruent. And yeah, we've got all 4 sides are congruent here. Really, really important to know that. And that actually makes our lives a lot easier as far as solving things, because we don't have to think about, okay, if this one is this long, how as long is that other one? It's just, they're all the same. I tell you one, you know all four of them. Okay, the angle property we haven't answered. Are all four angles here 90 degrees? No, that one should be very obvious that we've got acute and obtuse angles. We are not looking at 90 degrees. So now the diagonal properties. This is going to be a fun one. Diagonals are congruent. Do the diagonal lines appear to be congruent to each other? No, and that bottom one is really obvious. You can see, oh, let's draw it in. I guess that helps. Let's look at how long this diagonal is compared to the other. So very long diagonal compared to a short one. These are a little closer in length, but they're still not the same. So no, we can say these diagonals are definitely not congruent. But are the diagonals perpendicular to each other? Okay, and it's easiest to see that in the top two, where you've got a diagonal that's perfectly vertical and a diagonal that's perfectly horizontal. So we can see that if we kind of continue that thought with the other two rhombi up here, then yes, we can see that they are perpendicular. All right, and this is, I'll go ahead and tell you, a property that's going to be true of all rhombi. And we could kind of go through a logical reason why. And it kind of goes back to what we were doing earlier in the year with the perpendicular bisectors and angle bisectors and things like that. But let's just kind of work with it for now. So now we get to come to this last one. Are the diagonals angle bisectors?
No.
Do they cut all their angles in half? Turns out they do. So, and here's the reason why I added those little angle markers in. Look down here at the bottom one where I drew the open circles. These open circles are the same on both sides of the diagonal. And the open circle is just a representation to say, hey, this is maybe some specific angle. Let's say in this case it's about angle 80 or something. 70. Let's call it 70. Well, if it's 70 on the left, it's going to be 70 on the right. And it's going to be 70 degrees for both of those as well. So if we've got 70 degrees everywhere there's an open circle, then we can see it's being bisected. So I'll just kind of throw that in just as a, for instance. I'm not saying it's actually 70 degrees, but we can pretend it is. So all four of those are 70 degrees, and we can see that the diagonal is bisecting it. That's also true for the other diagonal. So yes, these are angle bisectors, and that's going to be useful to know. I'll go ahead and tell you with a rhombus, generally speaking, and not completely true every time, but generally speaking, if there's questions about angles, it's going to be a little bit easier to solve if you know the properties. I don't know what that was. All right. If you know the properties, these questions should be really easy. If you don't, you're going to be sitting there really struggling with it. But just come back to this. Look at what you know about the diagonals. Look at what you know about the angles. Well, really the diagonals are going to give you a lot of guidance here. Okay, so let's look at a couple of problems related to rhombi. And I'm going to mention right off the bat that F and G, I'm putting a star by both of those. Both of those require using the Pythagorean theorem. I'm just going to write that down over here. A squared plus B squared equals C squared. So if you want to try, you can do part of it without Pythagorean theorem. Well, not G. You need that from the beginning. But for F, you can do part of it without Pythagorean theorem. Part of it, you'll need it. So I'm just going to leave that kind of as a challenge problem. I already mentioned I'm not going to put Pythagorean theorem on the test, but it's good practice to try now. Okay, so let's look at some others up here. And I just wanted to look at problem C. And I mentioned if you know the properties of a rhombus, then these questions can be really simple. And if you don't, you're going to be sitting there maybe a little bit confused. So if we look at C in the top right, what which one do you think we could solve for first, x or y? What do you think x is going to be? 14. And let me walk through the logic in case you did not see that. So, and there's different ways of seeing this. So let me show you two different ways you could kind of figure out that that's going to be 14. One way is we know that the angles are being bisected, so this total is going to be 28 degrees. You guys agree? And we know opposite angles are the same, so this is going to be 28 degrees. And we also know that it's being bisected on the other side, so we divide it in two and we get our 14. So that's just using some properties. Really no complex calculations required, because we can figure that it's going to be 14 really simply. Now there's another way we could think of this. Maybe you think about the fact that a rhombus has congruent sides all around. And this is a weird one to think about, so you might not think of it this way. But if we've got congruent side here and here, we've just formed what kind of triangle? Isosceles. We now have an isosceles triangle. And if it's an isosceles triangle, then we know the base angles of isosceles triangles are congruent. So 14 and the x there are our base angles, so they have to be congruent. So again, different ways of thinking about it, but we can get to the same answer. That one's really not too difficult. I mean, I don't want to say it's not too difficult, but all things considered, I think students are able to find that one pretty easily. So for y, what are we going to do to solve for y?
14 plus y equals
8 angles of a triangle.
There you go. Okay, so the triangle sum theorem is one option. We can look at the fact that we have this triangle. We know it's an isosceles triangle, but for this case, it doesn't matter that it's isosceles. So we got 14, 14, and y. We could just add all those up, and they have to equal what? 180. So I'll just write that. 14 plus y will equal 180. Okay. And honestly, with the rest of these, I'm not going to answer that. You guys can do the actual algebra on that. But for the rest of these, you've got 4 more that are really good practice problems, 2 others that are good challenge problems if you feel like you can do the Pythagorean theorem. So finish C and then work on A, B, D, and E with the time that remains. I have the answer key up front. If you have questions, let me know. Because at the beginning, this can be confusing. But go back to those rhombus properties and see if you can figure out how to work your way through these.